I have a model here with two tetrahedral carbons in black, and let's say we have 4 hydrogen atoms represented by the white spheres, and let's say 2 chlorines by the orange spheres. And the question is, can I get a different isomer if I simply rotate one of the chlorines from up to down? Ooh, squeaky bond. Is that a different isomer? And the answer is no, it's not. But why should that be? Well, let's think about this single bond that's holding the 2 carbons together. I'm going to take the bond off for just a moment and replace it with 2 hybrid orbitals. Now these would be sp3 orbitals to form a sigma bond in between. And the point is that it doesn't matter the angle between the orange ones. They can be both up, one can be sideways, down, doesn't matter. That sigma bond is intact regardless of what angles the atoms are relative to one another. That's called free rotation around a single bond. Now, you need to be a little bit careful with that term because this model of balls held together by sticks is not really right. The atoms are touching one another and overlapping slightly. So if the orange spheres were actually really big atoms, there might be a little bit of hindrance as they try to pass by one another. But in general, we still have free rotation because it doesn't matter what angle they're at for the sigma bond to stay intact. We just saw where we can have free rotation around a single bond, but we do not have a free rotation around a double bond. How come? Well, now I've got a model with 2 sp2 hybridized carbons. The leftover p orbitals are shown on the right and the left atom by the loops above and below the plane of the molecule. And right now this molecule is in the cis conformation, with the 2 orange ones in front in the cis disposition and the 2 white ones in back. And if I want to rotate this bond, go from cis to trans, watch what happens. When I start rotating, say, the right-hand carbon, if I go halfway around, so the orange one is down and the white one is up, what's happened to the pi bond? It's gone away. Now these 2 p orbitals on the adjacent carbon atoms are in a non-bonding configuration. I've gone from a double bond to a single bond and eliminated the pi bond. Now that takes a lot of energy. It's effectively as much energy as it takes to break a bond. Now if I keep rotating, I can get to the trans conformation, the trans isomer now with the orange in back on the right and the orange in front on the left. And if you're thinking, well, now don't we have an antibonding configuration of the p orbitals? Don't worry about that. Because the electrons move much, much faster than the atoms do. So the electrons can actually reconfigure themselves readily and go back to the pi bonding interaction. So don't worry about bonding versus antibonding, but do worry about when you go from cis to trans, that is effectively the amount of energy it takes to break a bond, breaking that pi bond between the 2 atoms. We do not have free rotation here. So again, the idea here is that there is free rotation around a single bond. The carbon-carbon sigma bond is the same regardless of the angles of the chlorine with any of the hydrogens on the other carbon. When we're looking at Lewis structures, it's tempting to say that there should be multiple isomers, but it doesn't matter where we draw the Cl, since all of the positions on the right-hand carbon are identical due to free rotation. And putting the chlorine on the left-hand carbon instead of the right is also not a different isomer, since you can simply rotate the first structure to get the second. We don't have to break or form any bonds. It's different with a double bond. There is not free rotation. For example, upon going from trans to cis, you go from a double bond to a single bond back to a double bond. Breaking a pi bond takes considerable energy, more than a molecule will usually have simply moving around at room temperature. So essentially, the atoms are locked in place in either the cis or trans isomer. But it can happen with the addition of sufficient energy. For example, the basis of vision is the isomerization of cis-retinal to trans-retinal in your retina. On the left, there is a cis double bond, highlighted in red, that can isomerize to the trans isomer when it absorbs a photon. There is a significant change of shape which is sensed by the protein in which retinal is embedded. Exactly how that sends a message to your brain that you saw light is not fully understood, but the whole process requires light because there is not free rotation in double bonds.